All right. So we were covering a lot of the concepts, like the foundational stuff related to Q learning and the algorithms there. And these are like this is all really good knowledge to know. Like Q learning, like more or less, was definitely one of the most popular RL algorithms that was used a lot, even a lot in industry because it's kind of like relatively simple um, to be able to code up. And certainly be able to train. It's also pretty data efficient. So it had a lot of the ingredients that, for many applications, even robotics, that it would work pretty well. These days, it's true, maybe like PPO or reinforce only because of RLHF is becoming also pretty popular in terms of like most used RL algorithm, but Q learning is also up there pretty far. Okay. So so a couple of the nice parts for this algorithm and like why the industry and especially like robotics applications would benefit from this pretty well is one is that technically the algorithm does not, well, I'll say need on policy data. At the very least, it can train from off policy data and doesn't just have to rely entirely on policy data. So if the policy did collect at least like some data previously that was from the environment, it may never have to throw out that data. It still, at least theoretically, can learn from that data. That means it can be like pretty sample efficient. It's never really going to throw out data. Um, the challenge with this is it can be sometimes complex in order to be able to do exploration. You still need to collect a lot of data, even if it is more off policy instead of on policy. So off policy. And then often when the policy, so we still have to compute a policy from this. So this just means at some state, the agent or the algorithm that's been constructed needs to select the best action. So it can just do this argmax. So from the Q function, it's kind of not too much of a step just to be able to compute the best action from that, and that can be used. But the exploration that is most often used for like DQN and other Q-learning algorithms is typically epsilon greedy. It's really easy to code. So that's also one of the reasons it ends up working. And then as long as like an annealing schedule is used to start out from lots of exploration down to very little exploration at the end of training, it does tend to converge pretty well. And I think this as a bit of a reminder last time. So epsilon greedy is really just, select the best action with like 1 minus epsilon. So when learning starts, this might be something like 0.8, 0.85. And then at the end of training the policy, this should get down to like 0.2, 0.1. And that's when basically the best action will be picked more often because otherwise at the start, it means 80% of the time this policy picks a totally random action. And if it's trying to learn a policy and do this like estimate over the distribution of possible actions the policy can take, it'll get like a finer distribution of understanding its behavior later on in training if it's selecting more from the best action it takes. So this is a bit of a detail, but if you go back a couple of slides into being able to look at like the Q function is conditioned on the current policy, and the finer that it's like exploring less and exploiting itself more means that it's taking advantage of its like knowledge that it's learned so far. So it's actually maybe easier to estimate over that policy. At the very least, it'll have like a greater likelihood of being able to make it through some complex planning problems. Because if 80% of the time, like the robot is trying to complete a manipulation task, 80% of the time it adds total random noise to its like hand to be able to grasp something, it's just going to drop that pretty much all the time. So this is one of the other reasons why like exploration should be annealed over time because it makes it easier to get through these certain types of like plans or areas of the state space where like there must be consistent purposeful behavior, and any stochasticity that's added is basically like a total failure in the task. Okay, does that make sense? Questions? All right. Okay, so there's still quite a bit of like support. Um, I'll call it like training wheels needed for these algorithms. I don't want to use support because it's already a mathematical term that'll get confusing. So here, these deep networks, they might be doing value iteration or Q iteration or policy iteration, but how do these translate to like the deep part of deep RL here? So the nice part is for most of these algorithms, they transfer pretty well. So there's not too many issues in terms of like using a deep network, at least especially with some of these other algorithms, because they don't rely on as much bootstrapping. But we're going to talk here a bit more about the Q-learning case. Really very few algorithms, these other algorithms are not used pretty often, like value iteration or policy iteration are not used very often, but I will talk about one policy iteration algorithm at the end. So this is basically simplest version of online Q-learning. So it's just, collect some experience tuple from the environment by taking some sample, use this, single sample here to update the parameters for the network. So this tuple will have the reward that's used, the next state, still need to perform this argmax to get what would be the best action according to the current policy, and then just use this for training. Okay, so then how many people think this will work for deep learning? This, most simple version. Okay, nobody. There needs to, maybe. I mean, recently, yes, and we'll get to one paper on that, but this is exceedingly challenging to get working, like in a stable way. There's probably maybe some predictor for like only when an algorithm on my slides has at least 8 to 10 lines, then it might start to work because there needs to be like so many other band-aids around it to just make it a bit more stable in terms of deep learning training. Um, so one of the components that helps this learn better is to be able to make a replay buffer. So here, this is just taking the most recent bit of experience and then training the Q function on that immediately, which theoretically sounds nice. In practice, this doesn't work great a lot because the data that's being collected here from this policy is going to be highly correlated with the previous state, which really just means the data is not IID. It needs to be decorrelated just because a deep network is supposed to be trained on IID data. If that's the only, like if the guarantees on being able to optimize a deep network to some amount of convergence also say the data set needs to be IID. So this at least means this algorithm, not very, well, it's not IID at all. So then what can be added is this concept just called a replay buffer, which you might be a bit familiar with already. But now basically at the beginning of the algorithm, initialize a network, but also this, basically just think of it as a data set is what you'd normally call this in supervised learning. But in practice in RL, it's got a slightly different name called a replay buffer because it stores information and experience that the agent has basically collected in the world, and it gets to replay it in order to be able to train its model in the future. So then here, the slight change in the algorithm is now like roll out the policy to be able to collect some amount of data, stick that inside of what was this empty replay buffer. And then from this sample some batch. So this chunk here now looks much more like supervised learning. You've got some data set, sample a batch, do a training step, do this a couple of times, go back to collecting more data back in the RL loop. And then this, because this data effectively, like this batching process decorrelates the data with what the policy just learned, this makes everything more IID. So it's still technically not truly IID because the policy is still the thing sticking data in this data set, but it's unfortunately what I'll call IID enough for training to still be successful. And well, we'd have to have a whole nother class on what is meant by IID enough, but just sort of like trust me a bit for now. Although I think a lot of research papers also just kind of put a lot of trust in the reader because this is just used. There's not a lot of there's rarely a lot of theoretical justification for like how big to make this replay buffer. And as we'll get to the end of the talk, I'm going to introduce some of these things. And now most research kind of says it'd be great to not have to rely on these. Like it'd be great to actually just use this algorithm and not have to have so many other like support band-aids and kind of training wheels around this algorithm for it to work well. But that hasn't traditionally been the kind of recipe for success. So most implementations that you'll see of DQN online, they're going to have a replay buffer that typically stores about 1 million episodes, or sorry, 1 million of these transitions, sometimes more, rarely less. Okay, so makes sense. Any questions about this algorithm so far? Okay. So this ends up being, for a couple of reasons, pretty helpful, but I just wanted to like zoom out because this is like the pseudocode algorithm version of what I'm discussing, and now this is a little bit more of like the graphic representation where there's some world that's going on, some world that exists, some environment the agent is interacting. It's collecting some data that it puts into this data set. There's kind of like some other thread that's like learning from this data set, essentially like chewing through that data in order to get a better Q function. And then some sort of slightly separate, potentially separate process that's collecting data again in the real world and sticking that back into this data set. And this is also not entirely a new process. This, at least design here, has been around for like Q-learning for a while. One of the earlier papers on like fitted Q-learning was a great example of just doing this process. Um, okay, so the difference between what we'd normally think is a data set that we load into memory and at least what's used here, this is at least a buffer. Uh, what is it? It's a queue. So in this case, whatever goes into this data set, the thing that was put into that data set the longest to go is the first thing that leaves the data set. So basically the oldest stuff that was generated also from the oldest version of the policy. So in that case, that's almost like normally the most off policy stuff is the things that leave the buffer more often. Like I said, this should be large, around about 1 million samples, and be a bit cautious of keeping your computer memory limits in mind. So one of the most mundane bugs that I see happen kind of often is that you'll you can start training your DQ and like learning agent, and the algorithm will start filling this buffer, and then when it gets about halfway full, your computer crashes and runs out of memory. So this will grow in consuming the memory on your computer until it's finally full. So either be cautious of that, or there's definitely a couple of libraries I've seen that basically allocate all of the memory necessary for this buffer as soon as training starts. It's just full of zeros, basically. But then you won't run into this somewhat hard to detect bug, like why am I suddenly getting out of memory errors later on in the code, is one of the more difficult things to figure out why that's happening. So be cautious of that. Um, yeah. So in the opposite way of looking at this, the buffer still contains some data from previous policies. So this still makes it a bit on policy. Uh, so it can train with off policy data, but there's at least some amount of the data that's included in there should be pretty on policy. Uh, a bit of what ends up happening is actually a more on policy data often actually works a little bit better. And now there's this kind of weird boundary between we want some off policy data, but not too much. If it's too off policy, the Q function doesn't really give a good answer for that data in terms of Q value. If it's too on policy, then it's really not understanding that data too well, not really taking advantage of it being a Q function. Yeah, question. First in, last out, or first in, first out? Well, the opposite of this would be a bit odd because then like the first thing, I mean, putting this into a stack would be the kind of like okay, the opposite of a queue is kind of an on concept. But if the stack was used, that means that like the last thing that was in there ends up being the thing that stays in there the longest, and the first thing might be the first thing that's removed. But we kind of want to be able to keep around some, like it's best if what's in this replay buffer represents currently a good distribution of what would come out of the policy. So if we do this the opposite, that means it's the replay buffer really represents the oldest stuff that's kind of like least likely or least related to what the current policy distribution is. I guess if something was last in, first out, I don't know if the replay buffer would store anything because it'd be as soon as it comes into the buffer, it leaves, I suppose, so it doesn't store very much. So this depends a little bit more on the definition for the buffer, on like maybe how many things can be put into the buffer before something starts to get pulled out. So when this thing starts to reach, yeah, that's million, and then it starts removing things. But then it's basically going to be, you're going to fill this up with its first million samples of experience, and then the millionth and one experience gets put in the buffer and leaves, and then the millionth and second one gets put in the buffer and leaves because it's the last thing, like the most recent thing ends up coming in. So it's basically becomes a fixed data set. There are no, I just want to at least make one connection. There are definitely other ways to figure out how to pull stuff out of here. So sometimes instead of using first in, first out, sometimes people remove stuff that is like the poorest prediction for the actual Q function. So like has highest Bellman error. And there's also different ways of doing this where you can sample from this buffer and sample stuff from this buffer such that it has the highest reward. So like, why not train on the stuff that seem like the best? And sometimes these help, but they're also a bit different, bit difficult to balance in the algorithm because now you're biasing this data, affecting the IID assumption even more, so it's a bit more unstable. Yeah, cool. Uh, maybe I mean, you use the term less relevant data in terms of this. So the at least in the concepts here in this framework, when we want to talk about like most relevant data that ends up being the most useful, usually things that are more on policy end up being the most useful. Even like mathematically, because as data gets more and more off policy, it becomes a little bit harder. Like it's less in support in terms of what the current policy can estimate. Does that make sense? That's the hope, because the Q function is basically a Q function, but it's a Q function over some policy, which happens to be itself. So it's like it estimates Q values for stuff that's most on policy for what it just predicted. So that's at least like how I define, well, one way to approximate usefulness. Uh, There's other ways too, but that's a good start. That's at least most like general. Yeah. Other questions? Totally clear? Probably not, but we're going to go through a few more examples to get into some of the other odd corner cases in these algorithms. Okay. Um, okay. So one of these is having to deal with training over target values. So we had like even this process, I think actually that works fine for the algorithm. So this is still the most recent Q iteration algorithm that I showed. It just has a replay buffer now. But now this replay buffer, one thing to consider is kind of like what happens to this approximation, like this right side of this term, after an update is made to the Q function. Because remember, it's supposed to be a target. It's computing a Bellman error here. It's the idea is really to train like this side of the Q function to be able to reduce the Bellman error and have this match better. But there's this really problematic behavior that can happen here where basically if an update occurs that does update these parameters a little bit, and then it pulls the Q value of like the portion on the left closer to the reward plus future Q value. But if these two things are the same, maybe I'll do this. That means that after this update is made for the Q value on the left, it's very possible and extremely likely that the Q value on the right is also going to change values, like even somewhat uncontrollably, to try to push these together. And at least if we remember a little bit from last time, we talked about the fact that if we want our Q value and our Q like function learning to converge, it needs to be some kind of contraction, which means that like after an update, most of the like distances between all the outputs should shrink. So in this case, if this component here on the right can, change even a bit, or even worse than that, if it grows in any way, this is no longer a contraction. This means when like deep learning comes in here, there's no guarantees about how much these outputs change. And basically this can diverge wildly off to either like positive or negative infinity. They get NaN values pretty fast. So we need like a different mechanism to make sure, okay, we still need to ensure some type of contraction is going on here. So in this case, at least one of the nice options, sorry, these target values, like I was saying, can change significantly even after any gradient update. And like I said, the Q learning here may not actually be a contraction because it's chasing its own noise. So then what's done in a lot of algorithms is actually to introduce a concept called a target network. So this is even a little bit like it's more different than just using a stop gradient, because even if you do a stop gradient, it just leaves like this part fixed. Like the gradient isn't computed for the object on the right, but still the next time the component on the right now is now asked to be able to do some sort of prediction, it will have changed because it's sharing the same parameters. So now make another copy basically of the Q network, all the parameters that are included with the Q network. And this basically is supposed to be a somewhat older version of what are the current Q network parameters. And this basically helps reduce this noisy recursive dependence. And then it's possible for the algorithm to make many, many steps in being able to reduce the Bellman error. Still remains to be a contraction. And then there's just this last question that you might have. It's like, well, doesn't at least this target network need to be updated at some point? Otherwise, it's horribly inaccurate. So that part's true, but it should only be updated at a certain interval. So there's a couple of lines here, but really everything above here is the same. The only thing that's really changed is this. And maybe I'll write out some of the details. Oh, okay. No, there's a little change there, which is just basically this process. So basically, use a target network in order to be able to keep this right side of this function fixed. And then after, W steps, then copy what's the current network parameters from the like most recent version of the Q function that's been trained, copy that over to be this new target network, and then leave that fixed now for some number of other steps. So this is at least, approximately a contraction now. It's at least helping that process to make sure this can't diverge, at least as easily. So there isn't really a strong guarantee here that this doesn't diverge, but it certainly does a very good job at keeping the algorithm from diverging. And if your algorithm is diverging, you can make W of larger numbers such that this is copied over less often. Yeah. So in tabular Q learning, yes. When it comes to when you put a deep network as the function that's going to be used for the model, gamma isn't enough. So when you've got a linear model or you've got a tabular model, then it's mostly like, yeah, having gamma that's at least less than 1. And also technically the reward function needs to be a bounded function. Like it can't have values of infinity. And then, yeah, that can converge and be a good contraction. But here, basically whenever function approximation is introduced, nonlinear function approximation, a deep network, most convergence guarantees are now just up, like gone in a puff of smoke. Yeah. So here it's just we're doing this a bit more empirically and in practice because we know the concept is this should remain a contraction and like reduce over time. And then we're just kind of detecting corner cases. Well, okay, no, this particular optimization here can definitely make a step where now the thing on the right changes a whole bunch and it didn't contract during that update, and that's a problem. So we're trying to fix that even more. Hmm. Typically, there's only one target network used. So that's like for everything. It's not dependent on the experience buffer. Okay. Not not really. So if we like put this in the lens of it being a contraction, it's more about like the target network can be kept around long enough such that the contraction is still always a contraction. And then the contractionness is not really dependent on the size of the buffer. So often values for W here are somewhere between like 5 to 10,000. And after that many steps, then it's okay to do an update. Not really an update, but like a copying from the Q value function here to the actual target network values. Yeah. Okay. Other questions? All right. Let's see. I think that is actually written right here, but happens to go outside the screen. It's what I get for trying to add a little bit more detail to the algorithm last night, a little bit before checking this. But this says, yeah, like a good value for this W is about 10,000. And that I'm pretty sure is the value that was used for like the original Atari paper, the playing Atari at human level skill or something like that. I forget exactly the name, used values of about 10,000, even though the replay buffer was about 1 million in that case. Okay. All right, so now we've added a few more components to this diagram. A lot of this chunk is still the same, but now there's this target network process that'll be keeping around one set of the parameters for the network that'll actually be trained on all the time, and these target network parameters that'll be updated at some regular interval, and still doing Q function regression. The nice part is, 1 and 3 here are pretty fast. So this is like collecting data, like running stuff in the environment. Let's at least say in simulation is pretty quick. 3 is pretty fast in terms of learning, but so 3 is pretty fast, but 2 can sometimes now be pretty slow. So this target network actually introduces a lag in the way that the Q function is trained, because now it's got this other thing that's a little bit out of date in order to be able to estimate Q values. So it takes longer for these to both kind of converge towards each other. So this can slow down training a little bit, but good rule of thumb, is like, okay, we need the algorithm to converge first. Then we can start getting into the details about how to make it sample efficient. So convergence, still always like first requirement for an algorithm. Okay, so now that something is converging, now we're going to get into some of the details now to be able to make these algorithms even a little bit better. One of these is dealing with overestimation. So when the estimated Q value increases, shouldn't the agent's performance increase? It's supposed to be an estimate for actually how it should behave according to taking like an action at this particular state. But this, it doesn't always happen. There's a subtle detail in the way the Q function is being trained that actually makes this not totally clear. So here's an example of um, so this is what the agent, the red line is what the agent thinks it's going to do in terms of its performance. And the blue line, I'll just say it's a better estimator for it, but this is closer to how it actually performs inside of the environment. But we're kind of like wondering like, okay, why does this happen? And it has to do with a little bit of overestimation for this max overall actions. So here, going to introduce double DQN, where a Q function, it can be efficiently and pretty quickly be able to use to compute the actual Q value. And in some cases, you can get a pretty good estimate by looking over the argmax. But this like maximization operator here can cause some issues because, I mean, one of them is just like a deep learning issue. If this does a max overall actions, the Q function can just produce positive infinity for one action. And it'll always choose that one, even if it never took that action ever in the world for some reason. So it overestimates itself. Normally, training will reduce this over time. But really, when we're trying to do this estimation over these different actions, where all these are enumerated here, this is the type of expectation that we actually want to perform. However, what ends up actually happening, just like in the way that we're doing this max here, is we're really estimating this different Q function. It's like take a max over all the actions that currently exist, and that's the expectation, at least the way the policy's Q function is currently trained. And this can cause overestimation because basically an expectation over a bunch of max, a bunch of max of a bunch of different functions is always going to be larger than taking the max when it's an expectation over all these individual values. So it just means that like ignoring like Q learning almost entirely here. If you do this expectation and put it on like the outside of the max, you run into this problem. It'll always kind of estimate the highest value possible out of all the possible options, always. So this is bad from the point of view of being able to get a model that properly predicts how it's going to perform. It's good if really all you care about is trying to think that the agent will perform pretty well and never actually does any of those things. That's not actually good. That's a joke. Okay. So luckily, there is at least maybe one easy way to be able to reduce this overestimation. Is to use double Q learning. And what double Q learning actually means, since it's not a very informative name for this, is to actually use the online Q function to pick the best action. So before, when the targets were being computed here, the target function is what was being used to pick like what is doing the max overall actions for what'll be the target on the right side of that Bellman error we've been computing. We were using the target value. So it was kind of from itself picking its own best action in the future. Now what will be done instead is let's use the function on the left, which is like the online Q function, to at least be the thing that picks the best action. But still, the target function is the one that gives the Q value, but now it doesn't also pick its own best action. So it can't be quite as much of an overestimate of its behavior from before. It'd be kind of like instead of, some particular person saying like they're the best at doing this thing, well, maybe they're not. They've got a friend that knows them pretty well, and they're actually like, well, no, at this particular action, this in this area, this is your best action, and it's not actually that great. So there's at least sort of this double Q learning kind of now mixes together the way the two Q functions are used to be able to reduce this overestimation. Okay. Then if you want to know more about the details for this, you can go look at some of Van Hasselt's work. I think both of these should actually be Van Hasselt, and I shall go and check some of my bib file after this is done, but he sort of was the one who worked out some of the details for this overestimation. But these days, when you go to see, a Q learning algorithm in a library, almost always it's actually going to implement double Q learning. So just don't get as confused when you go to see that and see that these are kind of mixed and that the argmax for the Q function actually uses the online Q model as well. Okay. So now there's finally an algorithm that works. It can train pretty well. It doesn't overestimate too much. But when being able to do Q learning, there's kind of always going to be a couple of challenges that always exist. And this is actually in the community what's called the deadly triad. So it's really difficult in order to have an algorithm that can have the benefits of all these options. Because we want off-policy learning so that the model or the Q function policy can learn from offline data and it can basically be able to use all that information. It's also good to have an algorithm that can do like some amount of bootstrapping, because in that case, it also helps being able to learn off some of the other data. That's kind of just based off of the dynamic programming concept. That's kind of like a nice concept for being able to train a model. Or in the last part, we also want to be able to have an algorithm that has some type of function approximation, because then it can be used to like capture a really wide range of possible different functions that explain how the world works and then how to operate a policy inside of that world. The challenge is basically when all of these are combined, algorithms just don't work. So like if your function approximator is way too general, it's really hard to be able to train the policy, because basically after even when Q updates are being trained, the target network can still be pretty unstable. So like the more general that function class, the harder it is to train. And then if things are more and more off policy, the Q function that's supposed to be like conditioned over the actual policy that comes from that Q function becomes like less and less in support of itself then. So then it really doesn't estimate its current behavior very well because all the data in the replay buffer is actually from stuff like way back in time, and the policy doesn't perform like that right now. And it's sort of the same story for bootstrapping. So kind of like keep these in mind when designing one of these algorithms. There's basically a lot of research papers that try to bend some of the rules for each of these limitations by trying to make things more off policy. Well, then it becomes really challenging. So normally some amount of the algorithm needs to be on policy in order for it to still converge well, give or take. And then, yeah. So basically, if it's kind of like it's always easy to get two of these. So we can have algorithms for agents that are totally off policy and use bootstrapping, but they at least have to use like a linear model, not a function approximator. And then it's possible to have those other two. Or bootstrapping and function approximation can be used, but the data can't be so off policy. So it's kind of like can only get two of these in most cases. Getting three is, I won't say entirely impossible, but I really only know of a few pieces of work that have gotten close. Okay, does that make sense? This is kind of like the whole ugliness of RL, just kind of explained in terms of this deadly triad. And once algorithms are developed that basically rely on some of these other processes more, usually because there's some benefit for them, it makes the learning process more unstable. So, so training can diverge for a number of reasons from basically trying to be able to combine all these. But this also can explain like target networks help here. And then target networks are helping because, well, they help with the bootstrapping process for sure. Because then you don't have to worry about your model bootstrapping and then having it have sort of like wildly large differences in the errors that it computes from the actual model. Okay. So any questions about these algorithms so far? This is kind of like the foundational algorithmic stuff. Good for now. Okay. Yeah. Um, you certainly can. That was just covered a little bit more in the last set of lecture slides, but often, even for things I think in the Atari paper, they use n-step returns rather than just a single step. So that is often a method that's used for Q learning as well as for critics for policy gradients. And that actually, but that's a version of kind of making the data less off policy and a little bit less bootstrapping because now more information is being borrowed from long sequences for returns rather than from bootstrapping on its own model. So yeah, if we do n-step returns, then we're basically removing bootstrapping in that case. So yeah, it's in there, but yeah, good point. Didn't discuss. No, normally n-step returns will improve training because then at least the value estimates will be a little less biased. I talked about that a bit. So like in policy gradients and when we have a critic, that critic is usually like okay and a little bit of bias. Often Q learning critics are a bit more biased. I mean, even that was the whole last slide where this model way overestimates its performance, so it's extremely biased. It's not just like model error, it's like bootstrapping onto itself and inflating its own values. Okay, other questions? All right, then we can move past some of the foundational stuff. I know it might seem a bit boring, but like now we can talk about like the algorithms that are used these days. So if you didn't already go and update the slides for the class, because I basically added these in last night, then now there's a few more things we'll talk about, like, well, now what are researchers doing with trying to overcome like some of the deadly triad and versions of these algorithms. So you should be able to go and grab the updated file from the website, and there's just like an extra 10 slides at the end here. All right, so then one of the examples, like newer examples for this is to be able to make an algorithm. And here it's called Qt-opt. The task is basically be able to train a robot arm from vision in order to be able to grasp objects. So this is the idea is to be able to show like these methods work well in terms of variety of objects that the robot can learn to grasp, which is something that's pretty tricky. Because like prior methods for robotics and manipulation, they could be kind of specific to the arm. They may also be very specific to the object to grasp. Like it has to be a perfect cylinder or something like that. So here the idea is showing a bit more of the flexibility of like using function approximation and Q-learning in order to be able to get this to work. And then there's down here this workspace where there's a few objects it can grasp, not this entire pile. This is just like a sample of all the possible objects that were used. Okay, so this is, train a policy to grasp a bunch of objects. In this case, which we're going to talk more about in the next slides, but the policy for the robot is actually continuous. So far, everything we've talked about for Q-learning has been for like there's some discrete number of actions. So we can just quickly do an argmax over them, and there isn't really much of a problem there. So this means it's still going to use the same process, but they're going to do something a little bit creative with being able to maximize that Q function because it's just a Q value. Technically, we can just treat it as an optimization, essentially perform a type of policy iteration where it's just like, here's our Q function. The agent is at this state. Now just like query the Q function a bunch of times in the continuous space to search over that to find the best action. Technically possible to do, somewhat expensive at runtime to be able to do this sampling process though. But if it works, it works. So this is like the QT-opt algorithm is pretty simple to the diagram we saw from before. Collect a lot of offline data here for the robot, has some particular like replay buffer that it's sticking data into, some other process that's performing the Bellman updates. The one part that's at least a little bit, there's two parts that are different. One of them is it has a number of training workers. So at least for this project, they were maybe a bit more lucky. They had 16 to 20 robot arms that were all performing this task. So it's basically kind of like having 16 to 20 extra threads in the simulation that you're normally use for RL, collecting additional data. So that would help collect more data. And then here they're going to use a cross-entropy method just to be like, take the Q function and with the agent at this particular state, search over the possible actions to find the best action to try now. This has some other advantages too. So like now it's not assuming that argmax. So it's not going to overestimate itself as bad as just like straight Q-learning. But the kind of the price it pays is now the model needs to perform this optimization at every step to be able to compute the next step. So this inference time can be pretty slow, or it might not actually compute the max action because it needed more time to search over the Q function, something like that. But this can still, sometimes it's still kind of easy to perform this max overall actions in the continuous space. So it's not always super expensive. Yeah, and some of these models, they don't end up having to be an exact copy of each other models. This is supposed to be robots. So like this still ends up working out pretty well. And like every robot is never an exact copy of itself. So it still manages to train a policy, can grasp a variety of different objects across at least what I'll say are a small variety of different robot arms. Like the dynamics of them will be a bit different. They'll all have slightly different amounts of wear and tear. The bin will be slightly different. Although I know for the paper, they certainly spent some time like buying the same bin, lining up the camera to be pretty much the same camera point of view, things like that. That mostly helps with reducing the amount of data needed to be able to train the policy. Okay, does that make sense? Any questions about this paper? No? All right. Yeah, this was certainly one of the earlier papers that was just kind of like taking this template for deep Q learning. It was like, okay, great. Now let's actually get this working on a robot instead of a simulator. What other changes would be made? That's at least two of them. All right. So this one's a little bit different. This is what's called the PQN paper. And this kind of goes back to some of the assumptions from before. So if you remember, and it wasn't very long ago, so hopefully we all do, like target networks were not always a good thing. They do help convergence, but they also slow down the learning process because now it's sort of like having this extra weight or what are sometimes called like heavy ball methods or some approximate thing that's like the model's trying to be able to train itself to that, so it slows down the actual training process. So target networks cause this extra problem with bootstrapping. And also like replay buffers, remember they kind of help induce this IID behavior, but it does mean that the Q function is sometimes not always trained over the direct support of the best actions the policy would take right now after each of its updates. So both of these end up kind of, at least they're not the best solutions to have in order to be able to train a policy. It'd be nice to not require IID data, then at least the policy doesn't need to keep around as much data, so it consumes less memory. And to not have a target network would also be good because then at least training would be faster. So you wouldn't need as many gradient updates in order to be able to converge to the proper Q function. Okay. So then here, what the paper is looking into is kind of being able to take advantage of this and get this to work pretty well. Because part of the idea is, well, maybe one way of saying this, DQN was jealous of PPO and policy gradients. And by that, what is meant is like in those environments and those algorithms, it's possible just to like collect a lot of data, maybe quickly in a batch or all in parallel, do a policy gradient update and just keep doing that repeatedly. But DQN couldn't do that. It needed to keep around like a replay buffer in order to be able to collect lots of data to be able to decorrelate updates. But that also made the training process slow. So maybe in terms of a bit of this like jealousy, the process like, okay, can we make a Q-learning algorithm that actually like works pretty much in the same process as something like PPO or reinforce? So then it can still be pretty fast is actually one of the reasons for this as well. Because normally Q-learning is done in this sort of online learning fashion where it collects, well, no, this was the original algorithm I showed that was only a couple of lines that isn't really stable for Q-learning. DQN ended up needing like a replay buffer, and there's some extra stuff in here for target networks. So these are all like ways agents can collect data in the environment and some of the methods they'll use. So there's also a possibility for doing distributed DQN. It's very much like this paper, where it has 16 to 20 robots collecting data at the same time. But that can also make the optimization a bit more complex because now the data in the replay buffer is going to be more on policy. And that's sometimes going to be a bit of a challenge. And this last version for PQN, it's trying to really take advantage of vectorized environments and be pretty sample efficient. Well, being pretty wall clock efficient, to be honest. Okay. All right. Does that make sense so far? This is trying to be able to get this to train kind of quickly. Because really one of the problems with this original DQN method is it's not easy to be able to run in parallel to be able to collect data. That causes some problems. Hmm. So that is actually a bit of a tricky question. Uh, the answer to that question might be always, given what I'll show on the next slide. Like if we care about wall clock time and sample efficiency, at least for some of the experiments that they perform, which I'll get to in a bit, like it looks like PQN is actually faster at learning in many cases over PPO. With a couple of examples. So the kind of the idea was is trying to get a bit more of the advantages from Q learning here to have faster training, but still be able to train as quickly without needing a replay buffer and still work better than PPO. So in some ways, this was like, was it possible to make a version of DQN that would train faster than PPO? Yeah. Um, so like for vectorized environments? Well, good question. Doesn't totally bait you for this one, but it would work perfectly on this problem. So here it would be like maybe PQN would work well here. This could entirely be removed. Okay, technically PQN doesn't want offline data, so this wouldn't be used either. but the rest of these components could be kept and still be like trained pretty well without needing a target network either. But we haven't quite got to how it managed to get over the target network problem yet. Yeah. Yeah. I know that sounds maybe a bit unreasonable, but most robotics companies, that is entirely their game plan right now. Just like we need to manufacture some bare minimum number of robots and set up some environments to collect data, and then using like something like PQN as a better option than using something like DQN. Once once basically the process of managing to scale the data collection gets high enough, then it becomes more reasonable to use other algorithms. Even PPO in that case too. Like if you could collect data on policy across thousands of robots. So like maybe one subtle answer to your question is there's a lot of theory and things going on lately, but the thing that might actually achieve like a good boost in terms of robotics is kind of like making a company, something, such that you can get maybe about 10,000 robots out into the world and collect data. Maybe that's enough to meet the data collection needs to quickly train a policy for improving it. I have some doubts totally on that though, because otherwise I think some self-driving car companies would have solved that by now. But I also think in those cases they're dealing with a POMDP problem, not an MDP problem. So then they might need much more data than at-home cleaning robot that can just only turn on when people are not in the house or something like that. So in terms of like enumerating the data needed, it's more reasonable. Yeah. Question. Good. Okay. Okay. So yeah, but this is also common. We haven't really got to the sim to real part of the slides or like the class. But vectorized environments are also something that are pretty common, at least in RL libraries and especially in sim to real training. And it's just like instantiate 12 or like X environments, basically collect all the states from those as a vector, process them all through the policy so that you get, I'll use N now instead of X so it doesn't get as confusing, but like N environments in parallel, then you get N actions. You send all those N actions out to the policy. You get the new observations for all those N steps. So this is kind of like doing all of this in batch processing now. There's no longer send like one action out to one agent. It's always like large, matrices at least of states coming in and actions going out to the environments. So that means, remember, well, if you're more familiar with like GPU programming and what GPUs like, they like large arrays of stuff that are all put together. So this becomes very advantageous because it means you can like stick PQN and the environments all on the GPU, all process this really quickly and be able to train without ever having to leave the GPU, and it's all pretty fast. So that's one other reason to maybe like this, where it's maybe not so much of a little bit less of a focus on real world problems having to deal with robotics, but just like wall clock time, I want to try a variation of my algorithm. I want to run it in a simulator. You'll get a response, like a trained policy back faster this way. But we'll get to the sim-to-real lecture where this is going to have some caveats on like the types of tasks that work in simulation and some other challenges from what you can get there. Yeah. Question. Ah, exactly. Hmm. So yes, potentially. So I'll give the answer for PQN first, just so that we're clear there. Um, so here, this is just done in a single step. So it doesn't synchronize, has to synchronize anything because it's basically just sending the action to the environment. So it doesn't have to store a model for the policy as well in that thread because it's kind of treated as a matrix. There's only one policy. There's no desynchronization or like any asynchronous learning going on here. It's all like synchronous single step. But I think also like what you're getting at in terms of like, well, how would this actually work if you wanted to use it in the real world? Because at least one problem here, like that would exist here, or that would exist in the real world, but not here, is at least communication issues. Like, well, now if you want to send 4,000 commands to 4,000 different robots, there's going to be communication latency to send all those at the very least if the policy isn't stored on the robot. Or I think more to your example is like, well, the other option is to put a copy of the policy on the robot, and then there's less communication delays when at least making commands. And that there's trade-offs with both of these options. It sometimes depends on what type of task is being performed, on which one of these matter more. So if you want something that has more real-time control, often the policy needs to be stored closer and like on the robot. So it can have like 1,000 Hertz response time. But I will say that part of the plan for a couple of the recent foundational models for robotics companies is more uh, like OpenAI, ChatGPT API, where like there'll be some API that the robot just sends its observation off to and gets back in action. It might take round trip, like a tenth or half of a second, but that's less of a concern for some types of robotics tasks. Yeah. Does that make sense? Yeah. Other questions? All right, good discussion. All right, so then the last part about this, we've been kind of talking about the training process is part of the algorithm is to be able to reduce the reliance on target networks and actually get rid of them entirely. So instead of using target networks, they were actually able to get things to still converge and essentially still be a contraction using layer norm. And you can go into some more of the details in the paper, but essentially the proof in there is very similar to, yeah, like now looking at the dynamics of possible changes that can come out of the network after an update. They don't change too much, so then it's basically still a fairly well-defined contraction, so then it won't diverge. Probably a few other details in there to really get it to work. Um, yeah, so this basically like using layer norm, yeah, like I just said, it'll make the outputs of the target network for the model actually a little bit more smooth, a little bit more linear, so there's less issues with having to deal with divergence. And now, yeah, coming back to some of the results. So PQN here always seems to be the green line, where it does seem to be able to like perform and learn a policy pretty quickly. Keep in mind that for this paper, part of the contribution is also just great. It works without target networks and without a replay buffer. It also happens to do a little bit better than some algorithms, but the main point of the paper was not really like outperforming other RL algorithms because before just like this algorithm was considered impossible to be able to make. That being said, it still gets pretty good performance. Like after some tuning, the performance difference here is actually pretty tight, so not as big of a difference. But at least we can look at this ablation study a bit more. So this is just changing some of the methods that are used to normalize the outputs coming from the Q function. Uh, and of these options, layer norm seems to perform pretty good across a couple of different environments, although it seems like craft text is a bit of an exception here where, what is this? Next time I'll try and cut a picture that's a little bit more detailed. But this brown one looks like no norm, and then batch norm seems to work pretty well. I think there's a bit of a detail I've missed here in the numbering because I think this is still supposed to be green, but now it's a green dotted line, so it's some variation on layer norm because the blue line here is batch norm. And there's another green line here for layer norm. So I'll probably have to go and double check that one from the paper. But it seems like in most cases, some variation of layer norm helps dealing with the convergence problems. Yeah. Mhm. Hmm. I mean, those transitions may at least exist longer in the replay buffer, but it doesn't mean that the policy is going to end up selecting them from the replay buffer more in some way to make it more useful. So at least from like that logic, it's not clear if having a replay buffer allows the policy to like revisit those trajectories more than if it would just like rolling out its own policy again and collecting more data. Mhm. Mhm. So yes, if you added that in addition to this, that may help. I had mentioned for a bit that, and it's an approximation of this. Like maybe one way is to do like prioritized replay based on reward, but that doesn't necessarily mean that like uh, replay tuple based on reward like is one of these like key actions because maybe the agent needed to actually take less reward at some point in order to achieve higher reward later. So figuring out good prioritized replay strategies is still a bit tricky because you basically kind of like you need the Q value to understand whether or not it was a good thing to be able to replay. And this is in the process of learning it. So maybe it's definitely like a good concept to be able to dig into a bit more. But here, like having a replay buffer is still sort of like it's because it's a deep learned model. The idea is like a replay buffer is needed in order to make things more stable. But the replay buffer can also have like older data that's in there. So I guess I don't know. One way to be able to answer your question is actually to be able to compare these if there is a good trajectory in the replay buffer versus being able to collect more online data faster because vector environments can be vectorized. Which one of these ends up visiting, that trajectory that was of higher value more often? And at least from like some of these experiments that I think like QMix is a Q function algorithm, if we're basing it on performance and sample efficiency, it still seems like actually PQN is revisiting those trajectories faster if that's at least correlated with getting higher returns over time for the policy. But yeah, still good and somewhat complicated question. Great. Other questions? Good. Okay. So then this gets to the last piece, which is so a bit of those are about stability and being able to adjust the algorithms. This is a bit more about scaling. So if some people are familiar with scaling laws, which we've talked about only kind of briefly in the class, the challenge is there's not really well-formed scaling laws for reinforcement learning. It's a bit tricky to be able to come up with a good scaling law, like even in practice or in theory, partly because the model needs to deal with generating its own data to learn from and then learn from that. So these two processes make it difficult to understand the scaling law landscape pretty well. But this recent paper is at least shedding a little bit of light on how to handle possibly one way to be able to get better scaling for at least Q learning algorithms. Then what they're really proposing is to try a mixture of experts as a way to be able to add capacity into the model. And basically, as more experts are added, then the model grows in capacity. Okay, well, let me at least explain what a mixture of experts is. A version of this is if, there are a number of policies, action given s conda theta 0, and another policy a s theta 1, and there could be some number of policies. And the idea is these experts should all specialize in like some area of the state space. So maybe theta 0 will be good in this area of the state space. And then theta 1 will be good over here. And there'll be some other blob that's theta 3 that's good here. So it's kind of like as experts are added, they can handle the capacity of different areas of the state space to be able to learn well. Although I'll just say like a little bit more historically, this has still been really difficult to get working. But here it seems like if we're talking about capacity and like, if we normally think about scaling in terms of transformers and like covering tokens, here the models now are kind of splitting up their behavior in order to be able to cover areas of the state space. And maybe they'll scale a bit better. Okay. There's a few details that are a bit tricky in order to be able to get this working. So you can go read the paper for all of the details. There's at least one that I definitely want to spend a minute talking about because it's not so obvious to figure out how to make this mixture of experts. And by that, I might just mean, so I wrote down a couple of policies here, but how would you construct the network for a mixture of experts? Should they really be entirely separate with no shared parameters at all? Is that still going to scale well? At least when transformers are made and like those scaling properties are put together, like the transformer is kind of grown and it still shares a lot of parameter information inside of its own design. So at least having totally separate experts doesn't make any sense, right? So at least one way to get around this and what they used in the paper is a version of this. So instead of making in totally different networks, there was one single like encoding model. So it's kind of like handling all the perception. And then from that, the experts are actually a little bit further along when there's a dense layer of the network. We'll make some copies of that, and those can all be experts because they're more of experts now in like the policy space and planning, even though this chunk here might totally take care of the perception part of this problem. And this seemed to be, there's some details where you can look into the paper, but this process of being able to at least structure the network this way in order to be able to compute the experts seemed to be pretty helpful. Although they also had a soft version of this as well that would kind of like blend these experts together. But typically when you read stuff about a mixture of experts, the experts kind of act independently. Like one expert is picked and that expert gives an action. But then also what they did in the paper was like a soft blending between all of the experts, which can also like gives a bit more capacity, but can then also maybe help the policy learn a little bit better. So this is at least a little bit of a step towards being able to scale a bit better. Looks like I didn't, well, I guess this is some of the learning graphs here, where there's this baseline top one. It looks like this soft mixture of experts, the green line still ends up performing somewhat the best as like experts are added when trained over things in probably in Atari would be my guess. So remember this at least isn't totally always about sample efficiency. This is almost often just like ability to be able to get the best reward, just making a better model and then training it again over a lot of data and a bigger model result in better performance. And then how to realize those gains, because that's at least been part of the scaling law recipe for like transformers or what is like mostly imitation learning or autoregressive token prediction. Yeah, there's still more work to be done for RL. Yeah. Possibly, yes. But that, like having some sparsification of the network, kind of like goes against the idea for scaling laws, which is usually to have like more and more parameters that are all still connected and they're not really sparse, potentially. So like it can be helpful to have these sparse mechanisms because like actually they usually have really nice properties when we talk about generalization and normal like descriptions of functions. But even in this paper, after coming up with a mixture of experts, the version that seems to work the best is this soft mixture of experts. So it's not even sparse across experts in terms of what works well. So as much as it seems like we'd want sparse objects, it's either really difficult or too difficult to be able to train a deep network to sparsify itself properly. Or there's still something about that helps like model capacity to at least mix even in a light sense across parameters for the model to be able to learn. And this might also be even like partly related to what I was pointing out in the last class for homework 2, where like the model first learns the average behavior for like what's in the data set. That's kind of like a really simple model. It has really low bias, but pretty uh, low bias, no, high bias, low variance in that case, but it hasn't actually learned the details of the data set. And now to capture all those other little details about how everything goes on, it needs to actually have kind of a lot of capacity. So in some ways, when models are initially trained, maybe they're learning to like capture the mean pretty well and quickly. But after that, all the extra capacity is to figure out how to understand all those kind of like random small cases that also exist in the data set that the model still needs to cover in order to generalize well. But it takes a lot of capacity and a lot of data to still catch up on all those other little details that the function needs to capture. Okay. Other questions? Oh, all right, let's take a break for a bit. We're already at, oh my, 3 o'clock. Thanks for your patience. I guess we extended a bit long. Good. Yeah. Mhm. Yeah, we'll start up again at 3:04 just for extra info. Hey, how's it going, Daniel? Yeah. How was the paper chat this morning? Really sorry I missed that one. Yeah, I mean, Eugene does good work, and I know he's been thinking about that idea for 2 years and finally got some people to work on it. Hmm. Okay, good. Yeah, well, what is it? I guess $8,000 is considered a small amount of budget for compute because that'll be $8,000 per hyperparameter. Okay, I guess that's all right. Comparison. I suppose we can hope the price of compute goes down a little bit in the next year, so if that'll help. Mhm. I know that's sort of like a little bit of a concept that the community is trying to figure out. It's like almost whether or not to try and solve things explicitly, or is there a bit of an implicit way to get around to, like, if this implicit thing is done at scale, it needs to have that concept inside of it to be successful in order for it to learn stuff well. It's just usually even more complicated to figure out like what those implicit things will be that end up generating that behavior. That's why even when I chat with Chelsea Finn, was like did a lot of stuff in meta learning, but I was leaning more towards language models because it was just okay. Meta learning explicitly is like a version of the no free lunch theorem, and it's really hard and not very sample efficient. And like using a language model, you kind of like start with a more structured or a good representation that also works a little bit better, even though it's not explicitly doing meta learning. It's just implicitly doing really good representation learning. And that might be good enough. Seems to be in practice at least work a bit better. But that makes sense.